Okay, in this section, we're going to be taking a look at logarithmic functions, specifically their inverse relationship to exponential functions, which were covered in the previous section. In this section, we're going to be evaluating logarithmic functions, we're going to be solving equations with logarithmic expressions, and we're going to be graphing logarithmic functions, all requiring that we understand various properties concerning inverse functions. So that'll be a good place to start reviewing the properties of inverse functions. Okay, first, for a function to have an inverse, it has to be a one-to-one function, meaning that it has to pass the horizontal line test. So when you draw a horizontal line through the graph of a function, if it passes through that graph at one and only one point, that function has an inverse. The inverse can be found using the original function, switching x and y, and then solving for the brand new y. The third property of inverse functions is that when you are looking for the domain and the range of the inverse function, you can really use the domain and range of the original function, because the main relationship between the original and the inverse is that the responsibilities of the x and the y switch. So, since the domain and range has to do with x and y, this is a way that you can look for the domain and range on the inverse. I would recommend that you find the domain and the range on the original function first. Your domain on your original function will become the range for the inverse function, and the range on the original function will become the domain for the inverse function. So again, the x's and the y's switching responsibilities. Domain becomes range on the inverse, range becomes domain on the inverse. Also, at certain times, you may be handed two functions and asked to prove algebraically whether or not those functions are inverses. So an algebraic technique we can use to prove whether or not two functions are inverses is by using a composition of functions. And that's what you're seeing as property number 4 in the section that's called a brief overview of functions and their inverses. Property number 4 talks about this algebraic composition that we can perform. If you can take the inverse function and plug it into the original, simplify that algebraically and get 1x, and then also take that composition in the opposite direction, plugging in the original to the inverse and also get a 1x, then that is a proof that the two separate functions are actually inverses of each other. Additionally, when you go to graph, you're going to notice that not only in this section, but in every section where we have graphed and we've talked about inverses. This is not the first section. We've been talking about this since we began graph theory in chapter 2. When you graph an original function and its inverse on the same coordinate plane, you will see that a line can be drawn right through the origin. And that line is called y is equal to x. It goes right through the origin and has a slope of 1. And if you were to crease your paper, fold your paper on that line and open it up, you would have two matching images on either side of the line called y equal to x. So we say that if you have mirror images about the line y equal to x, which is just a mathematical way of saying mirror images on either side, then that is also a visual on the fact that the two graphs that you are displaying are actually inverses of each other. So some basic properties, but important in this section because, as stated, whether you are simplifying a logarithmic expression in order to evaluate it, or whether you're solving an equation with a logarithmic expression or graphing a logarithmic function, you will be using properties of inverse functions. So let's start so that you can see beginning with the definition of logarithmic function. So a logarithmic function is defined in this way. Y is equal to log of a value. That value has to be greater than 0, as stated right here. Like, for instance, if you allow it to be 0 or any negative number, it is undefined. So make sure that in order to keep your logarithmic function defined, that x value, now this happens to be called the augment, if that augment is negative or 0, it's, like I said, undefined, so it has to be greater than 0. This base, this is called the base, this number that's hanging down below the g, that base has to be greater than 0, and it cannot be equal to 1. This is the equivalent, and this is where the inverses come in. When you are rewriting this, you're actually using properties of the inverse. So you can rewrite the equivalent form of a log expression by simply pushing up the base, and you're going to write an exponential functions. Exponential functions are inverses to logarithmic functions. Just push up that base, go grab the item that is all by itself. It will become the exponent, and then the x will jump over and take its place. Now I've drawn a visual for you where each of the items in the original logarithmic equation, where each of those items moves as you try to transform it into an exponential expression. You're going to want to do all your problems from this position. They're going to deliver the original problem this way. You are going to transform it into an exponential expression, whether you are solving equation, whether you're graphing, even when you're just trying to evaluate it and you're trying to simplify it. So everything will be based on your ability to go back and forth between these two forms. Now here is more of a visual type definition, but these are equivalent. You're going to want to get it here. And again, all you're going to do is when it's in log form, the number that plays the role of the base while it's in log form, you're going to push that up and allow it to be the base again, but in exponential form. You'll grab the item that is on one side all by itself. It'll play the role as the exponent, and the x will go over and jump in its place. So basically, push that base up, and then these two remaining items, the augment and this y, they're going to switch sides. The x will come over and be by itself at that point, and the y will come over to be with the base, acting as the exponent. So let's practice getting those numbers in position, getting those items in position as we go from log expressions to purely exponential expressions. So here we go. Again, what it says up here is that you're going to push up this base at that point to exponential. So this log is gone. You're not going to be stating that at all. So we've already addressed the 7. It's going to play the role of the base. There's two items left at that point, the x and the 3. The x is going to come over here and be by itself. The 3 is going to come over to the side with the 7, acting as the exponent. So it goes right there. X comes over here. And there you go. You have taken that log expression and put it in exponential form. And putting in this form makes it much easier to figure out what the value of x is. You're going to need to get it like this in order to simplify anything like this. Okay, at that point you could just go to your calculator if they wanted you to evaluate this, which they don't. They just simply want to get you used to moving everything into the correct position as you go from logarithmic to exponential. Okay, likewise, here's another example here. You want to get rid of the log, so you're going to move things into position. This will still play the role of the base, but in an exponential position. You're going to grab the item that's by itself. It will act as the exponent, and this 25 will come and jump over and be in its place. So these two items switch sides. This comes over here to be with the b, and the 25 comes over and jumps in its place. And again, you go from something that really is undecipherable to an equation that you could actually solve just by observation. You could just look at this and say, what value squared is equal to 25? 5. So you're transforming them into equations where you will be able to continue if you were being asked to evaluate or solve. Okay, so this, one more. This time the log is on the left side, but it doesn't matter what side the log expression is. Just go after that base, push it up, go grab the item by itself because it's going to be the exponent, and then this number that's called the augment is going to jump over in its place. Now that one's actually decimal, so it'd be really hard to solve that, but that's why you're not being asked to evaluate it. They just want you to move things into place, the beginning of you being able to do all the rest of the problems in this section. Here you're going back the other way. So you're going to try and remember what you just did as you took your expressions from logarithmic form to exponential form. Think about the position that you moved each of the items into, and you're going to reverse that. So here we're in exponential form. Try to remember that this number that became the base, when it was in log form, it was also the base. So drop it back down. There are two items remaining. Remember, there was a portion of the problem where they switched sides, so do that again. This x will come over and be with the 12, but act as the augment. And the 2 will go over and take its place and be on one side by itself. Okay, so 12 drops down as the base, and then the 2 and the x switch sides. The x was by itself, no longer by itself. It's over here with the 12 and the log. The 2 goes over and takes its place. Okay, likewise right here, each of these is just an exercise in getting it back into log form so that we'll show you now to go forward and backwards. Okay, so here we go again. Introduce the word log. That base will still be the base, but gets written right down there. And the remaining two items, the 3 and the 8, will switch sides. The 8 will come over and be with the b, whatever side the b is on, but acting as an augment, so it's level with the word log. Put your equal sign. The 3 jumps over and takes the place of the 8, now being the item that's by itself. So this is equivalent to this. It's just that this is the form that we always want to get it in when we're asked to either evaluate and simplify or solve an equation. We're going to be working with or graphing for that matter. Okay, well, I'm doing it again. Just here we have a fraction, here we have a radical. So the numbers look a little more complicated, but it's the same thing. You have a base. On the side where the base is, that's where you want to introduce your log. So it's log. I mean, you can always flip-flop these sides, but on the side where the base is, go grab that base. It'll still be the base of the log, and then switch the sides of the remaining two numbers. The -3 will come over and be by itself, and this will come over and be on the side where the 5 is, the 1/25, acting as the augment of the log equation. Okay, then this, notice that each of these had a power, base to a power, base to a power, base to a power, but yet you don't see that here. So you want to get it in the proper form before transforming it into log form. So let's remember how you write a radical in exponential form. So you have to ask yourself, how does it occur underneath the square root? To what power? There's no power there, so it's said to be a 1. And when you want to get rid of this radical, you can write this in exponential form where the exponent will be a rational expression. So 1/3. Rational meaning a fraction. The exponent's a fraction whenever you go from radical form to exponential form. So this is really what you're working with. Now this problem looks like the other 3. It's got a base to a power just like you had here. Base to a power, base to a power, base to a power. So now we can go into log form. You can write your log whatever side the base is on. That base is still the base. Put your equal sign so you establish a left and a right side and switch the sides that these are on. So the 1/3 will not be on the side where the 8 is anymore. It'll be on the other side, but the 2 will come over and be with the 8. Okay, so now we've gone from logarithmic equations into exponential equations, and then we've gone from exponential into logarithmic form. Okay, now we're going to go a step further. We're going to be using the skills that we used in the first set of problems where we went from log form to exponential form, and we're going to take it a step further, actually going all the way to evaluating the expressions that we come up with. Okay, so this says evaluate each logarithmic expression without using a calculator, show all steps. Your calculator doesn't even do these anyway. It doesn't do anything other than base 10, so you have to know what this is, how to do them by hand. Okay, so when someone says evaluate, that means give the value that each of these is equal to. So right now, the value of log of 16, base 2, is unknown. It is some unknown value. I'm just going to call it x. Okay, now I'm going to use the skill on the previous page. I'm going to go from logarithmic form equation into exponential form equation by raising the base up, going and grabbing that item that's by itself so that it can play the role of the exponent, and then allowing the 16 to jump over in its place. So these two things switch side. I pushed the base up, and it's still the base, and then the x came over to be with the 2 while the 16 went over and took its place. And you can solve that just by observation. 2 to what power is 16? Well, that would be the 4th power. 2 times 2 times 2 times 2 would give you 16. So 2 to the 4th power. So that value that we're looking for right here is 4. And whereas that would not have been possible to figure that out while it was in this form, it is possible to figure out what log of 16 base 2 is if you put it in exponential notation, exponential form. Okay, likewise, we're going to find out the value of this. Right now, we do not know what this is equal to, so we'll just call it it is equal to some unknown value. Then I'm going to transform it into exponential form. So this base, I'm going to push that up, give it an exponent, which is going to be this x, and the 1 over 49 jumps over to take its place. By observation, I know that 7 to some power is 49, which is typically 7 squared, but because that 49 is happening in the denominator, that power has to therefore be negative. So it is 7 to the negative 2. That would give you a 49 in the denominator. Okay, moving to part C. In part C, we're going to again try to figure out what this value is equal to. So right now we'll just call it x, separate it from here. Then we're going to go 2 raised to some power called x is equal to this augment, which is 5th root of 2. Okay, now you see that on this side you have a radical and on this side you have an exponential expression. And what you're going to want to do in that case is get these bases to be the same so you can continue this problem solving it by observation. So as you recall, in this problem, let me point out a problem that was similar right here, where you had a radical, but you really needed it to be in exponential form, because everything we're doing in this section is us trying to relate exponential form to logarithmic form. So you want to take things out of radical form if you are given a radical in the problem. So this in radical form, again, ask yourself how many 2's do you see underneath the radical? Just 1. And to get rid of this radical altogether, you're going to want to write this as an exponent that's a fraction. So it's 2 to the 1/5. That takes us from 5th root of 2 to 2 to the 1/5. This is equivalent to this. Now we can solve this. When someone says 2 to what power is equal to 2 to the 1/5, well, if the bases are the same, the only thing that would make these completely equal is if the bases are the same as well as the exponents. Therefore, x has to be 1/5. Okay, moving to this one. Again, this is equal to some unknown value, and we continue in each of these examples to go from logarithmic form to exponential form. So that requires pushing up the base, letting this item that's by itself act as the exponent, and the 5 jumps over to take its place. So these two things switch side. The x came over here to where the 25 is, but as the exponent, and the 5 went over and took its place. Okay, this is going to require a little bit of rewriting, just because if you're going to compare this side to this side and figure out what's going to make them equal, have to match as well as the exponents. We got that to happen here. Here we figured out what this power needed to be by observation. Here we figured out what this needed to be by observation, what power would give us a 16. These two are easy enough to do that way. But then once we get to these more complicated ones, we're looking at trying to make the bases as well as the powers equal in order to finish off the problem. Okay, so we could rewrite this using a base of 5. So we could say that 25 is 5 squared. That 25 already had a power called x. And then it turns out that we now have 2 powers. That's called raising a power to another power, which requires multiplication. That's the power to a power rule. So we can now call this, what's on the left side, 5 to a power of 2 times x, and it mingles those 2 powers into just 1 power by way of the power to power rule. And then over here we have 5. Again, if you have 2 exponential expressions with the same base, the only way they can be completely equal is if the bases are the same as well as the powers. So we finished this problem figuring out what would make these 2 expressions completely equal by realizing that we still need to make these equal. 2x equal to 1, divide by 2, divide by 2, and you get x is equal to 1/2. Okay, so a little bit more work on that one. But you can't just do the easy ones, so throw some of those in there. Okay, then we come to some properties of logarithms that you're going to want to become familiar with. Namely, this first property gets used again down here, but in a more general sense. Let me make this a little bit bigger if I can. Okay, so this first property says that if the augment matches the base, you can see this is b as well as the base, then what this whole expression is equal to is whatever this power is. And that power is a 1, therefore that's why that's equal to 1. They did a little proof of it for you here. That if you were to write this in exponential form, you would have b to the first is equal to b. The definition of how to go from a log form into exponential form. Okay, so that property is going to be used. Okay, that happens again down here. Only here they start to tell you that this is called the inverse property, but it's really the same thing that you were using up there. These properties specifically have to do with the number 1, but this is how you can use it in the general sense. As long as this is the base, whatever this power is, that's what this entire expression is equal to. So if that power is x, all of this is just simply equal to x. You're going to be using that in a ton of problems as you go to solve logarithmic equations and when you're just simplifying them or evaluating them. Another property is that anytime you take the log of 1, that is equal to 0, and you could even put that in your calculator. This says the log of 1, any base, is equal to 0, just as long as you are fulfilling the restrictions for B that we discussed on the previous page. So log of 1 is 0. That you could get in your calculator. Here's another variation of the inverse property, which we stated was when the augment matched the base, those two take each other out with the word log, and whatever this exponent is what the overall value is. Well, this is just another way of rewriting that logarithmic property. I know this is kind of small, but again, if the base on this log matches this base on this exponent, then they basically take each other out with the word log, and all that's left is the value x, which is what the entire expression would be equal to. Now, I'm going to help you to identify these properties in the next 6 or 7 examples that I have that go with this. So in this section, get it to be smaller, you're going to evaluate each logarithmic expression without using a calculator. So you're going to be using these inverse properties that I just showed you, or the properties having to do with the number 1. Okay, this, you could look at this as the inverse property, even though it is mentioned here just concerning 1 and here in its general form. I don't bother memorizing those as 2 different properties. Just if this base matches this augment, whatever the power is right here, which is nothing here, so it's said to be a 1, that's exactly what this is equal to. So part A, there's barely any work. Part B, again, you have the same thing. You have this base, it's just that they're more, I guess, more complicated looking numbers, but you have base being square root of 5, you have augment being square root of 5. You have one of these here. It doesn't have like any power there, so therefore the power is 1. So that property says when the augment matches the base, take each other out, taking the word log with it, and whatever this power is, that is equal to the overall value of this expression. So this is also equal to 1. Here you may want to rewrite it in order to allow yourself to see what that power is that we're going after. But in parts A and B, the whole point was that the augment matched the base, and you don't have that happening here. You need to rewrite that to get it to happen. So if this base is 5, then you're going to want to rewrite this as 5 to some power, and that's easy enough. It's just 5 to the 3rd. You now have this in the form that where the inverse property applies. So you see that the augment matches the base. You basically take each other out with the log. Overall value that this is equal to is 3. Okay, likewise right here, you have augment matching base. Gone, gone, take the log with it, and the power is what this is equal to. Is what it simplifies to. Okay, all of those have been the inverse property. This one, you could make it fit the inverse property if you wanted to rewrite it, but you already have a property that directly addresses what you've been given here. Log of 1, any base, is just equal to 0. Okay, so that's that property right up here. Log of 1, any base is 0. Okay, here you don't have, it doesn't apply to, the arrangement of these numbers don't apply to the inverse property because you need to rewrite it just a little bit. If this base is 2, you use 2 to some power. So this is going to be log of 2. We discussed in a previous problem how to go from radical form into exponential form. So this would be 8 to the 1/3. That's because you have one of these 8s. Index is 3, so that's how it's written. We still don't have it applying to the inverse property. When the inverse property applies, it's because this matches this, and that is still not happening. So let's continue to rewrite it. Okay, we've got to get this problem rewritten in terms of 2's. So we could rewrite, leave that little base there, we could rewrite this 8 as 2 to the third. Don't forget it already had a power on it of 1/3. Now let's mingle those powers. In other words, raise this power to this power by applying the power to a power rule, which is just multiply the power. So we'll continue here with a 2. Then this is 3 times 1/3 is just 1. So this 2 now has a power of 1 on it. 3 times 1/3 is 1. Okay, then now we have the inverse property applying directly to this problem. Augment matches base. They take each other out with the word log, and 1 is what it evaluates to, what it simplifies to. Okay, last 3 down here. Nothing to do in this problem. You already have augment matching base, so those are gone. Takes the word log with it. This simplifies to 1/2. Okay, this was that variation of the inverse property. This base matches this base, and they take the word log with it. This whole thing simplifies to just y. Okay, that was this property right here. All right, and then this one is also that type of problem where you have a base and then a logarithm as the base on the log to match the base on the exponential expression. And this does match. I mean, it's given as square root of 9, but that's really 3. So this is really 3. And then the exponent is log of x base 3. And since this base matches this base, they cancel each other in some respects. Take out the word log. This whole thing simplifies to just x. So I've chosen one of just about everything you're going to see in the homework. Now we go on to the graphing. Okay, and in the graphing, you're going to be expected to graph by hand. You're going to be expected to know how to use those inverse properties to rewrite this logarithmic equation or logarithmic function in exponential form. Otherwise, you won't be able to create a table. Your calculator will do this, but it doesn't do this. So you need to know. And a lot of these problems, you're going to have both of the functions are going to be logarithmic functions. So you need to know how to rewrite it as an exponential, how to create a table, and again, how to reiterate all that you have been taught since Chapter 2 regarding domain, range, asymptotes. We're going to do all that. Okay, let's start with f of x. We're going to make a little table. Okay, so I have a column for x. Those will be the values that we choose for our exponent. I'm going to choose -2, -1, 0, 1, and 2. Get a nice full graph there. The y partner, well, y is equal to 2 to the x. So I'm going to have to calculate these things. Y is equal to 2. Oops, let me put this down here a little bit so you'll know what goes with what. Okay, so right here I'm going to figure out the answer for when I plug in -2 here. So it'll be y is equal to 2 to the -2, really equal to 1 over 2 squared. Whenever anything has a negative exponent, it is written in fraction form, bringing all of this into the denominator. So that's equal to 1/4. And you can write it as a decimal if you'd like. Okay, but there we go. We got the y partner for that one. Then we go to do this next one. It's y is equal to 2 to the -1, which is equal to 1 over just 2 to the +1. So that's 1/2. Then we do the next one, and it's y is equal to 2 to the 0. Anything to the 0 power is 1, so that's the partner that goes with that. And in this way, you're just getting the answers for each of these. Answer for that one, answer for that one. Now let's do this one. Y is equal to 2 to the 1. Show that you know how to make a table. You're in college algebra already. You always should be able to create your own table. Thus, the essence of showing your work, not relying on the calculator for everything. Later, when you get higher up in your courses, you may be able to do more with the calculator. Okay, so 2 to the 1, that will be 2. And then for this last one, the x value is going to be 2. So y is equal to 2 to the 2, and you have 4. Okay. So now we're going to graph this. And the graph here would be just plotting these points. We can go to -2 and up just a little tad, 1/4. Then we can go to -1 and go up just a little further to 1/2. Then we can go to 0 and go up to 1. Then we can go to 1 and go up to 2. So you see this graph climbing. And then we can go to 2 and go all the way up to 4. And so the exponential graphs that you saw from the previous section, we did a lot of these graphs, and a tail that hovers along a particular line. In this case, it's the x-axis, which has the name y equal to 0. That means this serves as the asymptote. This tail flutters and gets closer and closer and closer to this line, and therefore it also controls your range values. We need to state the domain as well as the range. So the domain here, don't forget that the domain is all about the x values on the graph. So the domain here, if you're just thinking about x's, these x's go all the way out to negative. And this leg right here, it may look like it goes straight up, but it actually gets wider and wider and wider. So we say that eventually the x values that are on this leg go out to positive infinity, which I'm not going to put there because I don't want to confuse it with the range. So negative infinity, and if you recall, all of your exponential functions had a domain of negative infinity to positive infinity from the previous section. When we do the y values, when we look at the y values on the graph, that means we are answering what is the range. The range are all the possible y values. So the y values on the graph here go to positive infinity, and then they go as low, but never quite reaching y equal to 0. They go from 0 to infinity on the y values. And I know it looks like this tail is pasted to this line, but it's just a smidgen above it. So such a small amount of distance in between this line and this asymptote that it's barely visible. So 0 to infinity on the range. Okay, now the asymptote is that line that this graph approaches. It is quickly approaching just infinitesimal amounts to this x-axis, and that is called y equal to 0. So your asymptote is always a line, and we name lines using equations. Y equal to 0 is the asymptote. Now, this logarithmic function is the inverse of this function. We have to write it, and you're going to see that as we write it in exponential notation so that we can create a table for this function so that we can then graph it, state the domain, the range, and the asymptote. You will see that they are inverses. Remember, when two graphs are inverses, they lie on either side of the line called y equal to x. In other words, they're mirror images on either side of that line, which is equal to log of 2 base x. Let's remember that this is the same thing as y, the function name. Over here we have log of 2 base x. I'm going to move this over just so I have room to do my work here. Slide that in a little bit. Okay, then to go from log form to exponential form, I'm going to raise up that base. I want that to look like it's a 2x, so let me put that a little lower. So raise up the base. Go and grab that item that's by itself, which is y, and then x comes and takes its place. Okay, but notice that now in this exponential function, the x and the y have switched responsibilities, which is always the case for two inverse functions. You used to have an x as a power in this original function, whereas now the y is the exponent. Okay, so now you have switched responsibilities. So in the table, you are always picking for the y value, for the exponent first. You're not always picking for the y value. You are always picking for the exponential value first. So here, the exponent was x, so we started by choosing these various numbers for x, whereas this time, it is the y values that we are picking, these arbitrary values. And these numbers that I'm picking, that I picked for x here, they're just small numbers, but they give me some sense of what's happening in the negative region as well as the positive region. So you're going to want to pick those same numbers, keep it small just like I did here, but for the y's this time. So -2, -1, 0, 1, and 2. And as you go and plug those things in, again, you're going to get 2 to the -2. Now, we've already done these values over here, so we already know it. There's no need to do it again. If you plug this in, it would be 2 to the -2. 2 to the -2 is 1/4. If you were to plug in -1 right there, it would be 2 to the -1, which is 1/2. So as I had stated previously, the x's and the y's switch responsibilities, and that's because this is the inverse of this, and that's one of the main properties of inverses. So if you know that that's what's happening, just switch these x's and these y's off this table that you just already did the work for. Switch these two and you have 1, 0, 2, 1, 4, 2. Okay, so 1, 0, 2, 1, 4, 2. And you have the whole rest of that table, but without going through this work again. Okay, go plot those. And as you plot these, you're going to go to 1/4 and then -2. About right there. And then you're going to go to 1/2 -1. 1/2 -1, so a little further to the right than that point is. And then you're going to go 1, 0. And then you're going to go 2, 1. And then you're going to go 4, 2. So you see that this time it is curling up this way. And this tail is getting closer and closer to the y-axis. Okay, so you have these two images. This one is f of x equal to 2 to the x, and this one is g of x, which is log of x base 2. This is the line called y equal to x, and every time you graph two inverses on the same coordinate plane, you will have mirror images on either side of this line called y equal to x. It's always the case, regardless of what chapter you're in or what kind of shapes you're doing. Two inverse functions will create that situation, that if you crease your paper right here, fold your paper and then open it up, you'll see the two matching images. Okay, so looking at this other graph called g of x and answering the same questions. What is the domain? Remember, the domain is, and the range has to do with the y's. But let's go back and again recall that brief overview of inverse properties that I went over when I started this section. And one of them was, again, the x's and the y's switch responsibility from the original to the inverse. That means the domain and the range switch responsibilities, because the domain is the x's and the ranges are the y's. So whatever the x's are doing in the original function, they're doing the opposite in the inverse function. So the domain here becomes the range over here. And if the y's switch responsibility with the x's, the range becomes the domain. So the domain is 0 to infinity. And you can even see that on the graph. Okay, those y values on this g of x graph go down to negative infinity, and this goes up to positive, because this leg flares up, up, up. Just keeps getting wider and wider and wider. And then the domain values are the x values, again on this g of x graph. X values are 0, anything bigger than 0, to positive infinity, because it goes all the way to the right. The asymptote, again, the x's and the y's switch responsibilities from the original function to the inverse function. So if the asymptote here was this x-axis called y equal to 0, then the asymptote for the g of x function, look at how that tail gets closer and closer and closer to this line right here, the y-axis this time, which goes by the name x equal to 0. So whereas the asymptote that the graph gets closer and closer to for the f of x function was y equal to 0, the asymptote for this one, the logarithmic function, is x equal to 0. Okay, so now we then have a graph for each one, a table for each one. We rewrote the law and we tried to use what we understand about inverses in order to cut down on the work, showing that you understand the theory behind inverses, the theory behind rewriting from a logarithmic function to an understanding how the x's and the y's change responsibility from the original to the inverse. Okay, moving to the next graph. These graphs that I'm going to talk about now have translations, and we've been talking about translations since chapter 2, just with different shapes. Now we're doing it on logarithmic shapes, but all the transformations are still the same. If you're going to have a vertical translation, that value will be found not with the x, but by itself. You do not switch the sign for any kind of a vertical translation. So if you see positive c, it's going to go upward c units. If you see negative c, it's going to go downward c units. However, when the value is combined with the x as one expression, that's a horizontal translation, and those must be switched. So if you see positive c, you're really going to look at it as though it's a negative c, and that makes it be that causes the translation to go c units to the left. If you see a negative c, you're really going to look at it as positive c, which would make the graph move c units to the right. Okay, then we had also talked about in previous sections what flips the graph over the x-axis as opposed to across the y-axis. When you are flipping the graph over the x-axis, the negative will be out front as a multiplier, as a coefficient. And when you see the negative inside with the x expression, that flips it over the y-axis. So this is a reflection across or about, they use the word about the x-axis. That means it flips it over the x-axis. When the negative is with the x, part of the x expression, part of the argument, it's going to flip it over the y-axis. These are all the same things from chapters 2 and 3, only we're doing it with the log shape. Okay, then you have these multipliers, and they are either a vertical stretch or shrink or a horizontal stretch or shrink, depending on where that multiplier is. When the multiplier is out in front, not with the c, as it is down here, these are considered vertical translations. and it will vertically stretch if that C value is greater than 1, like 1.2, 2, 3, 4, any of that, it's going to vertically stretch it. However, if that multiplier out front is some fraction between 0 and 1, like 1/3, 2/3, anything where the top of the fraction is less than the bottom, then that is going to vertically shrink the graph. Horizontal stretching, then the multiplier, that C value, will now be with the X. So it makes sense that it has an impact on the horizontal, has a horizontal impact on the graph. So if that value is greater than 1, it is going to horizontally shrink the graph. And if that C value multiplying the X is a fraction between 0 and 1, it will horizontally stretch the graph. So just a little review of things that we've been using since chapter 2 as we study all these graphs. Okay, let's apply that to these logarithmic shapes. Now we have two different log functions here. We're not graphing inverses. That's when you're going from an exponential function to its logarithmic equivalent. Then you're talking inverses. These are not inverses. This is just simply a transformation of this. So the translation that's going on here is a horizontal shift. And you're going to be asked to talk about these things. There's all kinds of questions that they'll ask in my math lab. What is the domain? What is the range? Not only on the original, but also on the transformed graph. So this is just bare basic bones log of x base 2, while this is log of x minus 1 base 2. So there's a horizontal shift going on here of positive 1, because remember you have to switch the sign. So that'll be, if you're thinking of the horizontal shift as really being positive 1, that means that this graph is going to shift 1 unit to the right. So basically that's an answer to this question. State the transformation required to go from f of x to g of x. And that is what I just answered right here. To go from f of x to g of x, you're going to see that after I get done, it will be 1 unit to the right of the original function f of x. So let's get at it. Okay, we're going to start off and we're going to try and make some, shortcuts here. How to read those transformations and use it to help us to make the second table rather than doing the work all over again. So we have f of x is equal to log of x base 2, but that can't be worked with. You need to put it in exponential form in order to create a table. So we think about the fact that this is the same thing as y. Over here we have log of x base 2, and then we put it in exponential form by pushing up this base, grabbing the item that's by itself, now becoming the exponent, and the x going here. Now I had already done the table for this on the previous page where I had gotten all the values for this particular exponential function, so I'm just going to use those values from the previous page. Okay, so when I did this same function before, I had done, remember you're always choosing for the exponent, the values for the exponent. I had done -2, -1, 0, 1, and 2. I had already gotten the x partners that went with it by actually doing the calculations. This one came out to be 1/4. This one came out to be 1/2. This one came out to be 1. This came out to be 2. This came out to be 4. Okay, and so then when we graphed this, once again, this was 1/4, but down here at -2. This was 1/2, but down at -1. And then we had done 1, 0 right there. We had done 2, 1 right there. We had done 4, 2. And when we connected these, we had this graph that went like this. and that got very close to the y-axis. So this is f of x equal to just log of x base 2. So we're treating that as the parent graph. If you want to go ahead and answer the questions regarding this graph, we have already done this on a previous page when we graphed this same function. The domain, in other words, the x values, all the x values on this graph are to the right 0. We're stating our domain in interval notation. The range, well, those are the y values. These are the x's. These are the y's. Okay, so the y values go as low as negative infinity, and this leg, even though it may not seem like it, stretches up, up, up. I mean, as you let this go further and further out, it just rises up, 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 so it eventually reaches y values that are in the infinity, that go to infinity. So this goes from negative infinity to positive infinity. Okay, the asymptote, well, it's this line that this tail gets very, very close to. That's where you're at. That's what's meant by your asymptote. It doesn't break through that asymptote. So this line that this tail approaches ever so closely is the y-axis, and that y-axis has a name. It is called x equal to 0. Okay, now much of what I have found here I am going to use to get the answers for the other graph. I'm not going to plug into this function after I transform it into an exponential equation. I am going to use what I know about shifting and how to easily get the values from the parent graph for the new, more complicated table. Okay, so now hitting the g of x function. G of x is equal to log of x minus 1 with a base of 2. Okay, if I was to write this in exponential function, remember this plays the role of y, so that would be y is equal to log of 2, x minus 1 base 2. And if I was to take it out of this unusable form that it's in, and transform it into something that would actually allow me to create a table, I'd have to take it to exponential form. So push this up, go grab that y, it becomes the exponent, while the x minus 1 stays here. And even that wouldn't be good enough. If I was going to create values into this equation, I need to get one of these variables by itself. The easiest, of course, the only one that you can get by itself is the x. You'd have to move this over here, at which point it would become a 1, and you would finally have x is equal to 2 to the y plus 1. But why go and plug? Again, we'd be choosing values for the exponent. Never choose values for the variable that's by itself. That is the dependent variable, and this value is dependent on what happens over here. So therefore, you must pick values for y. But why go and pick negative 2, negative 1, 0, 1, and 2, plugging them in one at a time and doing 5 separate calculations when you can just use your knowledge of shifting? If you can get that, you will cause yourself a lot less work. And so I've been stressing this. Okay, here's our table. We're not going to do the values all over again, but we're going to look and see what is the transformation here that we discussed at the beginning of the problem. In going from f of x to g of x, all that's happening is that there is a horizontal shift of positive 1. Well, you have to think about what that means. When you shift your graph horizontally has to do with the x-axis. So anything that's a horizontal shift impacts your x values, and only your x values. You are going to be adding 1 to each of the x values. Okay, add 1 to each x value. Why did I do that? Because in this graph there is a horizontal shift of positive 1. And that's exactly what that means, that each of your x values will be impacted by adding positive 1, whereas nothing happens to the y coordinate. Sorry about my dogs barking in the video, but okay, so back to that, a little bit of a noise disturbance there. In what's happening here, we said that we're going to add 1 to each of these x values, and we're talking about the x values from the parent table. And that is super easy to do. Just 1 plus 1/4. Well, 1/4 is 0.25. So that x value after we add 1 would be 1.25. The 1/2 after you add a 1 would be 1.5. The 1 after you add a 1 would be 2. The 2 after you add a 1 would be 3. The 4 after you add a 1 would be 5. So I've added 1 to each of the x values in the parent table, but there is no alteration on the y's. If there was any kind of a vertical shift happening here, that value would be out here. It would be like a +2 or a +3, something like that. But when the numbers are in here with the x, then they only impact the x, no impact, nothing happening on the y value. So what does that mean for this table? Just recopy these values as is. So in doing it this way, I'm not calculating everything all over again. I don't even have to have this. Telling you how to get out of this work if you're just doing a transformation that you're comparing to a basic parent graph. You don't have to go through all of this transformation if you just understand, hey, horizontal shift, it's impacting the x's. So let me just take the table from the parent graph and change what I need to change without having to recalculate all these values. And that's been a major theme since chapter 2, trying to get you to see that. Okay, we now have the values for the g of x function. Go and graph those. So this is going to be 1.25, -2. So go to 1, tiny bit past it, and drop down to -2. So there's 1 point right there. Then we're going to go 1.5 and -1. So a little further down to -1. Then we're going to go to 2, 0. So we're going to go to 2, 0. Then we're going to go to 3, 1. 3, 1. Notice that all these points with respect to the original graph, they're all moving over, just as we predicted. 2, and this is going to be 1, 2, 3, 4, 5, up 1, up 2. So this is 1 unit over, 1 unit over. Let's go ahead and connect these. This. And I want you to notice something before I flare out too wide on this graph. But this was the vertical asymptote for the original graph. And the graph that I'm graphing now is just simply 1 unit over. So the new the new vertical asymptote is going to be 1 unit to the right, just as all the points are moving 1 unit to the right. So my new vertical asymptote, this was the vertical asymptote for f of x. This is the vertical asymptote for g of x. And that line is called, get this out of the way, that line is called x equal to 1. So when I curl this tail, I want to hover right alongside of it but not break through it. Okay, so x equal to 1 is the horizontal asymptote for this. So now when we go to look at this new graph right here, we have domain. The domain this time is not from 0 to infinity. Concentrate on this new graph called g of x. That's right here. G of x is equal to log of x minus 1 base 2. That's this one right here. And that graph started at x values slightly to the right of x equal to 1. So it goes from 1 to infinity. The range, the y values on this new shifted graph go down to negative infinity, the y values, and all the way up to positive infinity. Okay, and just like we said on the table, nothing to the y's. That's different. However, the x values did get impacted. They all moved 1 unit to the right. Okay, as far as the asymptote goes, just discuss that there is a new asymptote on this graph. Instead of x equal to 0, as it was for f of x, for g of x, it is x equal to 1. Okay, so with that graph, we have everything we need there, and we've also discussed at the beginning of the problem that the entire graph shifted 1 unit to the right. Okay, regarding this graph. In this particular graph, we have log of x and log of 3 minus log of x. So again, we're going to use those translations to cut down on the work for the second graph. Okay, let's start with the first one. Now, when you see log expressions, log functions, you're either going to be looking at log, that's called common log, and whenever you don't see a base, it is said to have base 10. Okay, so when they don't hang a little base off of here, that is said to have base 10. Okay, so this one's base 10 also. So let's go ahead and get ourselves in exponential form so we have something to work with to create the table and the graph. So we have log of x. This is base 10, so that you understand that 10 is what you're going to be pushing up to put in exponential form. So it's 10, raise it up to an exponent. That exponent would be the y. And then over here is going to be x, creating a table. Now, we're not going to be able to use 5 different values because this will get the numbers will get way too big and run right off of it. I mean, you know, I could change the scale on the graph, but, you know, we already know what the logarithmic graph looks like, so we don't really need to use that many values. Remember, the values that you're plugging in are chosen for y, not x. Never choose values that's by itself. So I'm only going to go with -1, 0, and 1 this time, keeping in mind what the shape is. So when you put -1 in there, you're going to have x is equal to 10 to the -1, which is 1/10. Okay, when you put a 0 in there, you're going to have x is equal to 10 to the 0, anything to the 0 power, 1. When you put +1, so you can have 10 to the 1 is equal to 10. And we have that. So let's plot those points, get the graph, state the domain, the range, the asymptote. Okay, so here we go with moving to x equal to 1/10, so just a tiny smidgen beyond the y-axis, and then down to -1. Right there. That's where it's already getting really, really close to the y-axis. Then go to 1, 0, so 1, 0 would be right there. It's starting to curl and come up. And then we have 10, 1. So this is 2, 3, 4, 5, 6, 7, 8, 9, 10. And it'll be right there. And we already know the shape, so here it's starting to come and get close to the y-axis, acting as the asymptote. Okay. So this one's f of x. I'll label later because I don't want to run into anything that I'm going to do for the next graph. So the domain, remember, that's all about the x's. The domain here, what are the x's on this graph? Well, the x's go all the way out to positive infinity, and then they come as close as this line called x equal to 0. So these x values are everything greater than 0. So 0 to infinity. The range, which is all about the y values. Okay, well these y values on this part of the tail go down to negative infinity, and this tail, which looks like it goes straight out, but actually gets bigger and bigger and bigger, so those y values. Okay, the asymptote that you see this tail getting closer and closer and closer to, that's always the line that serves as the asymptote, is called x equal to 0, the y-axis. Okay, now we're going to graph the other one, but instead of doing all these values again, we're going to just look at what is happening in this new graph. Now you might want to rewrite this, maybe putting the log first and understanding that this negative multiplier right there, when the negative is a multiplier out in front rather than right in here with the x, that means you're going to flip over the x-axis, reflect about a horizontal line. And then we have what, a positive 3? Well, that's a vertical shift. So if you're comparing what is going on from f of x to g of x, these are the things that are happening. That negative right there means, so the multiplication by -1 is going to occur on the y values, because you see that that negative multiplier is not in here. So you're not multiplying the x's by -1, you're multiplying the y's by -1. Multiply by -1 on your y values. If we're verbally describing what that does to the new graph with respect to the old graph, it reflects it over the x-axis. Okay, not only that, there is a vertical shift. You have to know what variable do these transformations impact. Do they impact the x's or do they impact the y's? Okay, anything that's going to impact the x's will be hovering around the x variable. It'll be either something added or subtracted or multiplied, and then you know you're acting on the x variable. But otherwise, it's impacting the y values. So we already know we're going to multiply all our y values by -1 on this table. Furthermore, this 3 has nothing to do with the x because you don't see it encased in parentheses like this. So this is not something that's impacting the x's. Again, it is a vertical shift. So we are going to be adding 3 to the y values. What does that mean? It means that you are vertically shifting 3 units up. Because with those vertical shifters, we don't change the sign. We act upon them as they appear in the function. Vertical shift 3 units up. So you can expect that graph to move 3 units up and also flip over. Okay, these are all the things, but as far as what we're going to change in the table, we're going to multiply the y's by -1, and we're going to add 3 to y's. Now, since both of these things are being done to the y's, this is kind of like order of operations. You would always multiply before you add. So we're going to multiply, then we're going to add. Okay, do that first, do that second. You're doing nothing to the x's because these transformations don't indicate to do anything to the x's. Okay, so your brand new table, without actually plugging into this and doing those 3 calculations all over again in a more complicated function, just learn to impact the values that are already on your table. Okay, so concentrating on those y's, we're going to multiply by -1. So -1 times -1 would be 1, and then we're going to add 3. 1 and 3, 4. Okay, then again, multiplying the y's by -1, 0 times -1 is 0, and then 0 plus 3, 3. Moving down to that third y value, 1 times -1 is -1. -1 plus 3, 2. We're doing nothing to the x's, so what does that mean? Copy the x values from the parent graph as is. So 1/10, a 1, and a 10. Okay, moving along with this and plotting this. So this is going to be 1/10, and then on my x's, and then, but I'm going to go to 4. Okay, so this will be 1/10, but I'm going to my y value of 1, 2, 4. Okay, then I'm going to go 1, 3, 1, 3, 1, 2, 3. And then I'm going to go 10, 2. So I'm going to go all the way out to 10, and I'm going to be at 2. Right there. Okay, so here we go curling like this and curling up against that y-axis. And I will label these. So this is the g of x function, which is 3 minus log of x. And this is the f of x function, which is just log of x. Since there's no base, you can write it here or not, but when you don't write a base, we know it's a 10. Okay, so there they both are. And if you had to, state what the domain and the ranges and all that. Okay, the domain, let's see, the x's. We're talking about x's when we do domain. So the x values on this graph are, again, everything to the right of x equal to 0. This entire new graph that I just graphed are x values greater than or equal to 0. That's why we have a parenthesis, meaning it's anything greater than that. As far as the y values go, these y values go to positive infinity, and this would actually flare out. It doesn't go straight that way. I know they look like that, but if you continued graphing, that leg would go lower and lower and lower, bringing you to negative infinity. So those y values, again, going from positive infinity to negative infinity, because that leg would go lower and lower and lower. Okay, then the asymptote for this new graph that I just graphed. Notice that this new graph creeps right up against that y-axis. It has not shifted this way or this way, otherwise it would have a new vertical asymptote. But since this graph has not shifted to the left or to the right, it keeps that same vertical asymptote of x equal to 0. And of course here we already verbally explained what is the difference between f of x and g of x graphically. Okay, moving to the last graph, which I just selected, the other kind of log, which is called a natural log. And the only difference with that is that it has base e, the number e as the base. So when you see ln natural log, that base is said to be e. You want to go ahead and put that in there. Okay, so doing this first function in exponential form, it would be y is equal to ln of x base e. Being that it's a base of e, it would be e raised up to a power of y is equal to x. Okay, then making a table for this. Okay, now these are all decimals. You would have to go e to a power, and I'll demonstrate that in the calculator. I have some of those values already. Remember, again, you're plugging in for this. So let's get several values here just so you can see this. 0, 1, 2. Here put 0, here put 1, here put 2. Just as a demonstration, I'm not going to press them all in. We're running out of time here, but if you're going to do 8 to the negative 2, you would just come down this first column right here to the ln key. E raised to a power, as I demonstrated in the previous section, is a second function. So you're going to go second function E, and you're going to put in whatever power you're putting in, which is negative 2 in this case. And you get, let's just call that 0.14. We'll round it off to the 100th place. Likewise, you would enter each of these into your calculator. So for negative 1, it would be 0.37. For this one, it would be 1, e to the 0, anything to the 0 power is 1. And when you put a 1 in here, the number e is 2.72, but then it runs on and on. But we're rounding it off, so e to the first power would be 2.72 approximately. And then e is 7.39. I'll just do those values ahead of time. All right, then if you're going to graph, you would be graphing these points. So on the x-axis, go out to 1.14, which is just barely beyond the y-axis, and down to negative 2. So you can see it getting very close to this y-axis as an asymptote. If you move slightly to negative 1, so it's starting to move away from this asymptote called the y-axis. If you go to 1, 0, you're right there. If you go to 2.72, which is right before 3, 2, 3, so right there, you're up at a level of 1. And if you go to 7.39, you're up at a height of 2. So 2, 3, 4, 5, 6, 7, by 7.39, and up to 2. So again, you see that same similar shape for the logarithmic function. With the asymptote, it's getting closer and closer to that y-axis. So this y-axis, also called x equal to 0, which you have to name it, has an equation when given an asymptote. An asymptote is a line. Lines are named using equations. The domain on this problem is, let's see, all the x values on this graph are greater than 0, so 0 to infinity. The y values representing the range. The y values on this part of the tail go down to negative infinity, whereas this one, again, this leg right here actually looks like it's going out, but goes up, up, up to positive infinity. So those y values can be anything from negative infinity to positive infinity. Okay, asymptote is this line that this tail hovers close to. It doesn't break through. So that asymptote, being that it's a line, is named using an equation, x equal to 0. Okay, when you are asked in that last sentence, also state the transformation required to go from f of x to g of x. Well, you can tell that just right up here. This is a horizontal shift of negative 5, meaning that the whole graph is going to move 5 units left because it's negative. 5 units left. That's one of the things that happens when you're comparing f of x to g of x. The other thing is this number not being odd with the x, that means it's a vertical shift. You don't switch the sign on the vertical shifters, only on the horizontal shifters. So vertical shift is negative 2, meaning you're going to move 2 units. Vertical means up or down, so when it's negative, you're going to move down. Okay, as far as how do these things impact the brand new table that I'm going to make, because I don't want to do these calculations all over again. I want to work with what I have here and use these horizontal and vertical shifters, use any kind of transformation that's being, that I'm being prompted into. I want to use that to transform this table so that I have a lot less work to create the brand new table that goes with this. So yes, I could rewrite this as an exponential function and go and plug in all these numbers again and do all those calculations and enter them all in the calculator. But the simpler way is to understand that when you have a horizontal shifter of -5, what does that really mean? It means subtract 5 from your x's. That's what horizontal shifting is all about. So you're going to subtract 5 from your x's on the parent table. Being that you also have a vertical shift of -2, well, the vertical shift is all about the impact on your y values. So this means subtract 2 from your y's. And these are the two things that are going to get you out of rewriting this as an exponential function and then plugging these values into that new exponential function all over again, because that would be a ton more work. Just like when I was talking about this problem on the previous page. Sure, you could rewrite this whole thing you can rewrite this whole problem as a function, an exponential function, and you could reevaluate it all over again. But that would have been a lot of work. Same thing for 2 problems back. I actually did show you how to rewrite it as an exponential function, but totally not necessary. Understood that all that happened in this problem was a horizontal shift of +1, meaning go get that parent table, add 1 to all the x's. Horizontal always meaning it impacts your x. So we're trying to get away from doing this when we're doing 2 graphs on the same grid. Trying to get away with having to go through the work of evaluating both functions, just as I am doing in my 3rd problem here, where I'm just kind of stressing the same things. So let me raise this up just a little bit so you can see more of it. Okay. All right, so creating this new table, and that's even my y's over 5 different values that we went after here. And again, I'm just going to act out this horizontal shift and this vertical shift by doing the subtraction that's necessary. First, let's do the x's. We're subtracting 5 from each of these x's. So you can get your calculator to help you with that. You can just go 0.14. 0.14 minus 5, you get -4.86. Let's just do all the x's first, then we'll do all the y's instead of switching back and forth. Then we have 0.37 minus 5, so -4.63. Then we're doing 1 minus 5, which is -4. Then we're doing 2.72 minus 5, and that's -2.28. And then we're doing 7.39 minus 5. And that's 2.39. So we have all these brand new x's, and I got out of plugging into this, and I got out of writing it in its exponential form. Everything we're supposed to be doing is subtracting 2 from the y values. So the y values are just integers. You don't really need to play with it. If you want, plug them in. So anyway, -2, and then you subtract 2 would be -4. And then -1 take away 2 would be -3. Then 0 take away 2 would be -2. Then 1 take away 2 would be -1. And 2 take away 2 would be 0. Okay, so getting out of a lot of work there. Plotting, we can plot and then talk about the domain, the range, and the asymptote. We've already discussed what happens. These are kind of questions you'll be asked in my math lab. What does what is happening with respect to the graph. So this verbal description is what you're going to want to check off. Moving 5 units to the left, moving 2 units down. And they'll either ask you if you're doing it vertically or horizontally. So getting this other graph almost out to -5, 1, 2, 3, 4, 5, that's slightly before it, and down at -4. Okay, then we're going to go to -4.63, which is slightly before that, and down to -3. Going to turn. Then we're going to go to -4, 1, 2, 3, 4, and down to -2. And then we're going to go to -2.28 and -1. So -1, -2, slightly beyond that, and down to -1. Right there. And then 2.39, positive 2.39 and 0. So that's going to be 1, 2, slightly beside it, slightly past it, and right there. So this. And then again, before I draw this tail right here, let's look at what that new vertical asymptote is. I mean, this y-axis is the vertical asymptote for f of x. But the vertical asymptote for g of x is what? You have to look at the shifting that goes on. Notice that everything in this graph is horizontally shifting. Every f of x to g of x is horizontally shifting 5 units this way. That means the asymptotes as well. So if the asymptote was at x equal to 0, it is now at x equal to -5. 1, 2, 3, 4, 5. So I'm going to put it in place just so I don't flare this other tail out too far, and let it guide the tail that I'm about to draw right now. Okay, so there's that asymptote, and then this tail just flutters right alongside of it, but never actually touching it. Okay, so that can help me to talk about my domain, and can also help me to name my asymptote. Okay, so the domain for this new graph called g of x is everything greater than 5. So it starts right here to the right of 5 and goes all the way to infinity. The range, well, the range values in this particular problem, it did shift up, but this graph still goes from -infinity to positive infinity, because again, this leg goes up, up, up. And then the asymptote, well, that's what helped us not to make this tail over here too dramatic. So that was called x equal to, the name of this line is called x equal to, actually, -5. I need to stick that -5 right in there. Properly named. -5 for this asymptote that guides the tail on g of x. So we've done everything, we've done a lot of graphs, and talked about how f of x relates, cut down on the work by doing the table for the easier function, and then looking at what kind of transformations are going on in the more complicated function with respect to the easier one to help you get the table, but without doing all. Okay, last page of this is a few more of these problems where some of them are asking for domain, some of them are asking to simplify, some of them are asking to solve an equation. Okay, so with the domain, again, I want to point out that this augment must be some number greater than 0, because the minute it's equal to 0, this log is undefined. And you can try pressing in your calculator log of 0, you'll see that it's undefined. And also, if you have any negative numbers, it's undefined. So that's exactly how you find the domain, by keeping this entire expression in the augment greater than 0. And then just solve it. So this would come over here being a -6, so x is greater than -6. What does that mean in interval notation? Well, if you don't know how to state it in interval notation, draw a picture of it. Here's -6. Here is everything greater than -6. So it would be -6 to infinity. Okay, then state the domain of this function. Remember, this is just a natural log where the base is e, not that we need to know that in order to get the domain. Because for natural logs, as well as any other kind of log, this augment needs to be greater than or equal to 0. So you start there, then you solve it, bring the 4 over here, it would be -4. That would leave you with -x greater than -4. And then when you're solving an inequality, if you're going to divide on your last step, divide or multiply by a negative, that makes this switch. The direction of inequality switches. So now -x divided by -1 is just +x. This switches from a greater than to a less than. -4 divided by -1 is 4. In interval notation, less than 4 looks like this. If you need to show yourself on a number line, do that. Less than means all of these, so -infinity up to -4. Remember, when you're doing up to 4, when you're doing interval notation, you have to say the smaller quantity first, followed by the larger quantity, such is the case here and here. Okay, here you're evaluating, trying to get you to recognize, since it was such a major theme in this section, the inverse property, where the base has to match the base here, and sometimes that requires rewriting the number. First of all, you see no base here. That means it's base 10. As we refer to as a common log, and when you are given a common log with no base, it is base 10. Well, if it's base 10, oops, I wrote it in the wrong place. If the log has a base 10, then you want to rewrite this augment using base 10 so that you can get the inverse property to apply. So this is the same thing as 10 to the third. Okay, when the augment matches the base, they take each other out with the log going with it, and that entire expression is equal to 3. Okay, likewise here. ln never has anything other than a base of e, so not much to do there. The augment cancels the base, taking the log with it, and this entire expression is equal to 2. Okay, last few problems here. You're going to be using another major concept taught in this section, how to go from logarithmic form to exponential form. Okay, that requires you pushing up the base, going and grabbing the item on the other side that's by itself, which will now be the exponent, and this jumping in its place. So this jumps to this side, 4 takes its place. Those two items, after you push up that base, those two items switch sides. So the x minus 5 comes over here. You now have a little equation to solve. 2 to the 4th is 16. And then you have x minus 5. Bring the 5 over here, at which point it'll be positive 5. And you have x is equal to 21. Now make sure that with these solutions, that the solution that you're giving, it may not make this augment 0 or negative. Okay, your solution must, otherwise you have to throw it out and say it's not a solution, must keep the augment greater than 0. It cannot even cause it to be 0, or you have to throw it out. So this is fine. 21 minus 5 is a positive number. It has to result in a positive number. Okay, same thing here. We're going to take that base, raise it up. using this as the power and the x taking its place. So push up that base and then switch sides with these two remaining items. Negative 2 over here, x over here. Okay, 6 to the negative 2 is just 1 over 6 squared, or 1 over 36. Try to write it in the most simplistic form possible. Okay, this is not a number that would make this augment 0 or negative, so it is fine. It is the solution. Okay, last problem, finally. Sorry about the long lecture, but this is pretty new and pretty strange for students at this level, and it continues to be a weak spot. So we want to make sure that you're being given ample illustration of the examples. Okay, so again, same thing, same concept as what happened in these previous problems. It's 2 raised to a power of 3 is equal to x squared minus 7x. Again, push up that base. This comes over here. The 3 comes to this side. Okay, so this is going to be 8 is equal to x squared minus 7x. This is a second degree equation, therefore all terms should be on one side. You're going to attempt to either factor it or use the square root property. So I moved this over here, became a negative 8. This is easy enough to factor and quicker than using the quadratic formula, so I'm going to factor this. Okay, when you go to broke up the x times x is x squared, and breaking up the 8, it would be 8 times 1. Making the 8 negative and the 1 positive. Okay, x times x is x squared, that would be the negative 8, positive 1. Added to that would be negative 7x, and that would be the negative 8 in the back. So I'm just quickly checking that I factored it properly. I have. I'm checking it by FOILing. Now make these little equations using the zero factor property and solve them. This gives you x equal to negative 1, which might be a solution. This will give you an answer, x equal to 8, and that might be a solution as long as it doesn't make the augment 0 or negative. So when you put negative 1 in here, this would be negative 1 squared. That's 1. Take away negative 7 times negative 1. So 1, that would be 1 plus 7. This is fine. If you put an 8 in there, that would be 64 minus 56. This also results in a positive. So your solution set contains both of these. You don't have to throw either one of them out. Here your solution set is 1 over 36. I don't know if they're going to make you put it in solution set notation. Probably not, but if they do, this is it. Okay, that concludes the lecture for section 4.2.